Can I start? Yeah. Good morning, everyone, and welcome to this advanced workshop on high performance and high throughput computing with Quantum Espresso. I am Stefano Baroni. I am the old character of the crew which has been organizing these kinds of events for more than a decade now. So I have been given the honor to start the school, and then I will be kicked away. I will disappear in the background. I will be around, nevertheless. So this is thought to be an advanced workshop, which means that you are supposed to know the basics already of what we will be talking about, particularly the theoretical basis. So most of the workshop will be concerned with advanced technical aspects of quantum mechanical material simulations using a specific approach, which is not the only one available out there, but we will focus mainly on the plane wave pseudo-potential approach. This being said, we have to start from somewhere, and just to establish a common dictionary to which we will stick and which will allow us to communicate with each other, I will try to give a brief and quick overview of the concepts and the words that will be used throughout the next 2 weeks. Traditionally, these schools are very informal, which means that in spite of being recorded this time, nobody would object if you interrupt the speakers and you ask questions whenever the speakers are not clear enough, whenever they assume that you know things that you don't know, and in spite of the inevitable diversity of your background. So some of you may know more about some topics, some specific aspects. Some others may know more about something different. Someone may have already a stronger background than others, but we are here to learn. And if we don't succeed to teach, if we don't succeed to get understood, we will fail. So please don't let us fail. If we are not clear enough, you simply stop us. You wave your hand, and the speakers will make what they can to let themselves understood. Okay? So let me start by a few very, very general statements about computer simulation, computer modeling, and the different ranges of phenomena to which you may think of apply computer modeling. So nature and our own experience is characterized by a variety of length and time scales. This is the way our cognitive functioning works. We measure lengths, we measure times, and physical phenomena occur on specific time and length scales. So the macroscopic scale is the scale typical of our human senses, what we can perceive directly with our eyes, our ears, and our touch. And typically, the length scale is of the order of a fraction of a second up to few milliseconds, dozens of milliseconds, and up. Likewise, lengths that we can perceive are of the order of the millimeter and up. In this realm, if we want to describe mathematically the nature, we have to use classical mechanics. There are quantum phenomena that occur at the sensible scale, but they are very exotic, and we will not be concerned much about them in this school. So this is a scale where we can assume that the Planck constant is simply 0. On the other limit of this rough sketch, there is the atomic scale that is characterized by times that are typical, that run from femtoseconds to nanoseconds, and the length scales that are around the angstrom or 10 angstroms, or that is a nanometer. This is the realm of quantum mechanics that is, for most applications, well decoupled from the classical limit. And we know rather well how to deal. We have a well-established theoretical machinery and computational machinery to describe this nano world, as well as we have, and we have had for centuries now, a machinery to describe the classical world. In between is a kind of terra incognita. Very strange phenomena occur, and this is an emerging field of science about which we will say very, very little, but not because it is not interesting. Actually, it is very interesting, but because we will be concerned with a more well-established set of phenomena occurring at the atomic and the molecular scale. I have a simple homework for you, just something to think about, and you may want to think and revert to me or to other instructors to propose an answer to this. The homework is a quiz. It is, how is it that time scales go hand in hand with length scales? That is, how is it that when phenomena occur on very tiny length scales, they are usually very fast, and when they occur on very long length scales, they are usually slower? There is not a well-defined correspondence, of course. There is this is a broad picture, but there is a very, very little occurring up here and very, very little occurring down there. There is a general explanation that I would invite you to think about and to revert to us if you have any answer to that question. Different time and length scales require, as it is obvious, different theoretical approaches. Going from thermodynamics, finite elements, and classical electromagnetism in the classical regime, that is the realm of engineering, we will be mostly concerned with the opposite side of this picture on methods based on electronic structure theory. And in between, there is a continuum of methods that go through from electronic structure methods to dynamical methods based on electronic structure, that is ab initio molecular dynamics, and then up to classical models for interatomic interactions, classical molecular dynamics, and stochastic methods, all the way up to hydrodynamics and classical methods. But as I was saying, we will mostly stick on this leftmost and lowest corner of this graph. Of course, different sizes and different durations require different accuracies. If you are requested to measure your own weight or your own height, you don't need a nanometer accuracy. You don't tell your doctor how many nanometers are you told. And different accuracies in turn require different approaches. As in the laboratory, if you have to measure any property to different accuracy, you may use different instruments, different apparatuses. Likewise, in theory, different accuracies require different theoretical approaches. Going in terms of low accuracy, that is appropriate to systems that are larger and that last longer. We have classical empirical methods. Then we introduce a little bit of quantum mechanics, and we may want to use some quantum empirical methods or quantum self-consistent methods that we will be mostly concerned with, in which we fully account for the quantum nature of the atomic and molecular constituents, but we treat quantum mechanics with some kind of accuracy. We don't treat explicitly the full complexity of inter-electronic correlations. This is the realm of quantum self-consistent methods, down to when and where we may want to describe the full complexity of the quantum behavior using quantum Monte Carlo, quantum chemistry methods such as MP2, couple clusters, or configuration interaction, or methods based on many body perturbation theory such as GW and the Bethe-Salpeter equation. In our 2 weeks course, we will mainly focus on quantum self-consistent methods and methods based on many body perturbation theory using algorithms and methodologies that, as the title of the school indicates, are distributed with the quantum espresso suite of codes. So, quantum espresso is all about ab initio calculations. What are ab initio calculations? So those are a set of methodologies, not just one specific methodology, but a set of methodologies aimed at simulating the properties of materials using Schrödinger and Maxwell equations and chemical composition as the sole input ingredient. By sole, I stressed the word sole because ideally we want to avoid any explicit input from experiments. Sometimes we will use some common sense that will require direct use of experimental information, but generally we want to avoid as much as possible input from the experiment. Why? The main reason is that not making use of experimental information gives us an unbiased description of what we are doing. That is, not using any prior knowledge on the system make us believe that we may be right or wrong, we may be accurate or less accurate, but in an unbiased way. That is, we are led to think, to believe that we may treat on an equal footing systems and processes that we know, as well as those that we don't know. And this in scientific, in science is very important. We don't want to learn what we already know. We want to learn what we don't know, and we have to use methods that are believed to be as accurate where we don't know than they are where we know. Of course, what we know is very important for validation. It is important to make us believe that these tools that we use are accurate. Whether or not are accurate, this is another story, and this is something to validate which requires lots of effort and lots of pain, and the conclusion is the methods that we will be using these 2 weeks that are mainly based on density functional theory and to some extent on many body perturbation theory are believed to have a high degree of accuracy, and this is something that cannot be deduced from the equations. This is something that can only be tested, validated by comparing the predictions of our models, the predictions of our methodology with what is measured in the lab when we know what is measured in the lab. When should we use ab initio methods? Well, not everywhere and not every time, and not because it's your job. Your job is not to use one methodology or the other. Your job is to ask significant questions and give meaningful answers. So you should use ab initio methods when currently available approximations, they are not perfect, so they are approximated, make the calculation that you mean feasible, and the results meaningful. This is important. Feasibility depends on technology, depends on the availability of computers large enough and fast enough to solve the equations that you want to solve for the systems that you want to address, and to provide the meaningful results. This is important, guys. I have too often heard people your age, or even my age, that when questioned about the meaning of their calculations, that were doubtful because it was known that the approximations that they used are not very accurate for the systems that they address. And when questioned about this, they would answer, there is no better approximation. And so what? So if the approximation that you use is not enough to solve the problem that you have, you choose another problem. You don't spend your valuable human time and the expensive computing time to apply a theory that is unable to provide the meaningful answers to the questions that are being raised. This is very important, very important. There is plenty of important problems. If the problem that is given to you cannot be solved accurately, you change the methodology. If the methodology does not exist, you invent it. If you are not good enough to invent it, you change the problem. And how? Using digital computers, as you learn to do, clever algorithms, it's important. The progress that has been done over the past few decades is often attributed to technology, to the Moore's law on the availability of computers of increasing power and capability, but even more, it is due to our ability to devise algorithms of increasing cleverness, increasing complexity to address those problems. Common sense, it is important. It is important. You have not, so theories and methods do not escape the rules of common sense. If you cannot describe what you are doing in a few well-chosen words, this means that you have not understood what you are doing. So common sense doesn't mean being too simplistic, but means that you always have to have a grasp on what you're doing, and you always have to be able to explain what you are doing to a little child. If you are not, to some extent, if you are not, this means that you are not really understanding what you are doing. And scientific rigor. Scientific rigor is something that is never appreciated enough. You'll get you are being trained to use very powerful machines that produce an incredible amount of information. If you have not an ethics of your thought, if you have not an ethics of what is useful, what is not, what is accurate, what is not, what can be tested and what cannot, it would be lost. Science wouldn't lead anywhere. So I think you have to train yourself to be as rigorous as you can be, whatever rigor may mean. So let us come to the real to our real business. We want to simulate the behavior of materials using quantum mechanics, and the holy grail of quantum mechanics. What is it? It's the time-dependent Schrödinger equation. It's the wave equation for a system of interacting electrons whose coordinates will indicate very hastily with lowercase r. The nuclei have coordinates that we'll call uppercase r, and here you have the nuclear kinetic energy, the electronic kinetic energy, the interaction potential that involves nuclear and electronic degrees of freedom, and of course the wave function, the very complicated object of quantum mechanics that depends on an enormous amount of variables, because you have one coordinate for each electron, one coordinate for each ion. You have an Avogadro number of ions in the tiniest grain of sand. You have a few dozen more electrons for each nucleus. So it is a very, very complex equation to solve. So complex that in practice you cannot solve it. The first important approximation that has been devised in the 30s by Born and Oppenheimer is that because the nuclear mass is so much larger than the electron mass, and no less than 2,000 times heavier for the lightest nucleus, that is the proton, that is the hydrogen nucleus. Then to a first approximation, you can neglect the nuclear kinetic energy with respect to the electronic kinetic energy, because the ratio of the electronic to the nuclear mass is very, very small. By neglecting this, you can map this time-dependent Schrödinger equation to a time-independent Schrödinger equation for the electronic degrees of freedom only. You see here you have just the electronic kinetic energy. You have neglected the nuclear one, and you can solve for each set of nuclear coordinates the Schrödinger equation at clamped nuclei. If the nuclei are clamped, the matter stays still, and you can derive lots of information from solving the time-independent Schrödinger equation. Of course, nuclei do move, and where does the nuclear dynamics go in this picture? It's conceptually simple, so it should be derived. I won't do that, but conceptually it's very simple. Heavy objects, as we all know, obey Newton's equations of motion, right? We are heavy. The objects that we manipulate are heavy, and they obey Newton's equations of motion. So nuclei in the Born-Oppenheimer approximation obey Newton's equations of motion, and very significantly, the force that enters these Newton's equations of motion for the nuclei are the derivative, the gradient of a quantity that you can interpret as a potential energy, and not surprisingly, this potential energy that regulates the nuclear motion is nothing but the eigenvalue of the electronic time-independent Schrödinger equation at clamped nuclei. Because the nuclei in that equation, so the nuclear positions in that equations are parameters, every property of the solution will depend on that parameter, and so the electronic wave function would depend parametrically on the nuclear coordinates, and so will the eigenvalue that acts as the potential energy in the classical Newton's equations of motion for the nuclei. To compute that effective interaction between amongst the nuclei, in principle, we'll have to solve this monster time-independent Schrödinger equation for electrons that interact among themselves and with the nuclei, which is something that you simply cannot do for the reasons that we have just mentioned. There are way too many electrons to consider. And even when the systems are small enough, for instance, a small molecule, the fact that the electrons interact with each other, that the nuclear electron potential that comprises the interaction amongst the nuclei, the interaction between nuclei and electrons, and the electron-electron interaction. Because of the existence of this electron-electron interaction, you cannot factorize the electronic wave function as a product of one particle wave function, so this makes the problem basically untractable. This is the concept of inter-electron correlations that I'm sure all of you will be to different extent familiar with. And density functional theory is basically a formal framework that allows to replace the complexity of the electron-electron interaction with an effective potential. This effective potential is a one-body potential, so it is a potential that only depends on the nuclear coordinates, but does not depend on the mutual distances amongst different electrons, but it depends on the electron density distribution. It depends on, because this potential does not depend on the electron-electron interaction, you can, if you think that the electrons move in this potential, then because they don't interact with each other, each electron would have its own wave function because they are independent. So there is a Schrödinger equation for each electron independently, and you can define a density distribution as the sum of the square moduli of the one electron wave functions, and the effective potential will depend on that one electron wave function. So this will lead to the celebrated Kohn-Sham equations, where you have one electron wave functions that obey a one-particle equation, but the potential of that one-particle equation will depend on its own solutions through the density here. So let me very briefly, oh gosh, we are really behind of time. When did I start? 9:45. Okay. Density functional theory owes its name to the mathematical concept of functional. What is a functional? It is a function in the mathematical sense, an application whose argument is itself a function. So it is an application from a set of functions to real numbers. examples of functionals, I have listed here a few trivial. For instance, the value of a function at a point is a way of associating a number, a real number, to a function, the integral over a domain, or the integral of the squared of the gradient over a domain, or you name it. Any rule that allows you to associate a real number to a function is a functional. Ways of approximating functionals include the standard discretization of functions. So that is the way Volterra, who was the Italian mathematician who first introduced functional analysis in the 30s, I believe. A way of approximating functionals is would be to discretize the function over its domain of definition, and you have thus that a function that has infinitely many degrees of freedom would be discretized by the value it acquires at discrete values of its argument, and so a functional would be an ordinary function of the value that the argument that the function has at specific values of its own argument. So in this approximation, a functional would be represented by an ordinary function of very many variables. Another way of representing functionals, which is very much used in our community, is to expand the argument over a basis set. So a function of the functional argument as a whole would be nothing but an ordinary function of the expansion coefficients. So we use computers, and every time we represent a mathematical concept, we always have to devise ways of representing those mathematical concepts on a computer. And basically, all the possible ways would boil down to discretize continuous objects. A function by itself is a mathematical object that depends on infinitely many variables. X, it's the variable, is the argument of the argument. You have to discretize it in a way or the other in order to be able to compute. Of course, you have to generalize. So once you have mapped a functional onto a multivariate function, onto a function of many variables, you will want to do calculus. And to do calculus, you have to extend the concepts of elementary calculus, the main of which is the derivative. The generalization of partial derivatives to functionals will be functional derivatives. I will not say much about this, but basically every time you hear of a functional derivative, you have just to close your eyes to figure out how the functional is represented as a function of a finite number of variables, and when somebody tells you this is the functional derivative of this or that, you have to think actually this is the partial derivative of the discrete representation, is the continuous limit of the partial derivative of the continuous representation of the discrete representation of the functional. How many of you have ever heard about Mr. Hellman and Mr. Feynman? Who knows what is the Hellman-Feynman theorem? I do. Please raise your hands. Most of you do. So I will. That's very good. I will skip the first transparency that I wanted to dedicate to this subject. Oh gosh. Okay. So basically, here you have the Newton's equation of motion that I mentioned before. Says that the acceleration of the nuclei is equal to the force acting, is proportional to the force acting on them, which in turn is the derivative of a potential energy surface, which in turn is the eigenvalue of a time-independent Schrödinger equation. So, gosh, wait, this is not what I wanted to do. How to start again here? Okay. So the general problem is, given a Schrödinger equation whose Hamiltonian depends on a parameter, in this case the nuclear coordinates, how to compute the derivative of the eigenvalue. This is the eigenvalue, the derivative of the eigenvalue with respect to the parameter. I had to prepare one of the few slides with equations that I will not go through because most of you know what it is. The few who don't, please come to me and we'll go through the steps of the equation at the coffee break or in the afternoon. The take-home message is that the derivative of the eigenvalue is the expectation value of the derivative of the operator. Remember this, memorize this as a memo, as a memory aid. Hellman and Feynman say that the derivative of the eigenvalue is the expectation value of the derivative of the operator. Very important, very useful, ubiquitous in molecular simulations. But much, 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 much more general than most of you would assume. And for this generality, I will spend one full slide on. The validity of the Hellman-Feynman theorem is usually established in terms of matrix algebra, linear algebra, and similar stuff. This was the content of the slide that I just skipped. But conceptually, the real root of the Hellman-Feynman theorem comes from the existence of a variational principle. Since all density functional theory is about variational principles, I want to take a few minutes to elaborate about this concept. You all know the Ritz variational principle, right? The Ritz variational principle says that the ground state of any Hamiltonian is the minimum over all the normed wave functions, all the wave functions whose norm is equal to 1 of the expectation value of the Hamiltonian. A similar property exists for excited states, but it's a little bit more complicated because excited states usually are not minima of anything. They are just stationary points. They are saddle points. All the mathematics would hold nevertheless. But for the sake of clarity, let's concentrate on the ground state, where this is not an extremum. This is the bona fide real minimum. Okay? So the energy as a function, the ground state energy as a function of an external parameter can be seen as the lowest line eigenvalue, that's fine. But this can also be seen as the solution of a variational problem, which implicitly or explicitly we always do in our professional practice of molecular simulations. So let me abstract a little bit this concept. Suppose you have a function or a functional. This is a functional of psi, right? Because psi is a function, and this bracket is a way of giving a number out of a function. So it is a functional. So let me rephrase this in a slightly simplified but more general way. I have G. G is a function or a functional of an argument, x, that takes the place of psi, and some parameter lambda. And I call lowercase g of lambda the value that that functional acquires at the minimum. You see, it's just the translation, the generalization of this concept, okay? E of lambda, what is it? Is the value of the minimum. So you trace away, you take away the argument psi, and you just take E of lambda, the value of the minimum. So you try to generalize this. Think a little bit more abstractly. G of lambda, E of lambda is G of lambda, is the minimum over all the wave function psi x of a function that is a function of x and lambda. And the question is, what is the derivative of lowercase g with respect to lambda? Let's do some simple calculus. The value of g of lambda is the value that capital G acquires at the minimum, and the minimum is given by the solution of the equation dg over dx equal to 0. This is how you search minima, right? So g of lambda, lowercase g of lambda, is equal to the value of capital G at the solution of this equation. Let us now compute the derivative of lowercase g with respect to lambda. Lowercase g depends on lambda in two ways. Explicitly, because capital G depends on lambda, and implicitly, because the solution depends on lambda. Let us apply the chain rule. G prime of lambda is equal to x prime of lambda dg over dx, computed at the minimum, plus the explicit derivative. But the first implicit term vanishes because of the condition of the minimum. So Mr. Hellman and Mr. Feynman would say that, remember the quantum chemistry formulation, the expectation, the derivative of the eigenvalue is the expectation value of the derivative of the operator. Now I will be a little bit more general. The derivative of the minimum only has contributions from the explicit dependence of the minimum on the parameter, and not on the implicit one. If you apply this to this functional, you just get the ordinary Hellman-Feynman theorem. But this is much, 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 much more powerful, because it has nothing to do with eigenvalue equations, it has nothing to do with Hilliard algebra, it has just to do with the existence of a variational principle. Very important, ubiquitous. This is a kind of Swiss knife of physics. You can use it all over. You can solve lots of problems with this very, very simple concept that I like to call the Hellman-Feynman theorem, although very few people would call it Hellman-Feynman, but it's exactly the same thing. It's really exactly the same thing. Now, density function theory. This is the many-body Hamiltonian whose eigenvalues as a function of the nuclear coordinates are the holy grail of our molecular simulations, because they are those that determine molecular stability and molecular dynamics. Now, you can think that the energy, the ground state energy of a system moving of a system of electrons in that Hamiltonian is a functional of the potential. This sounds weird, sounds complicated, but it's obvious. The fact that the ground state is a functional of the potential is nothing but the fact that you give me the potential, and if I'm good enough, I solve the Schrödinger equation. So the Schrödinger equation is uniquely determined by the external potential. Hence, by definition of functional, the ground state, the eigenvalue, is a functional of the potential. Right? Simple. This functional, you can write, so the energy, this functional is the minimum over all the possible normalized wave functions of the expectation value of these three terms. I separate the first two, kinetic energy and electron-electron interaction, and the expectation value of the potential, the external potential, because the external potential, by definition, is a one-body, is a one-electron operator, then you can write the expectation value of V like the integral. V, you see here, you have very many variables, one for each electron. But you can integrate out, because this is the sum of functions that depend, of equal functions that depend each one on one electron coordinate only. If you do a very simple algebraic step, you will be able to rewrite the expectation value psi v psi as the integral of V of r with just one variable, not one for every electron. One symbolic variable in whole times a quantity that I call rho of r that embeds all the integrations that I have skipped formally. This rho of r is nothing but the integral of the square modulus of the many-body wave function with respect to n minus 1 of its variables, where n is the number of electrons. This is the charge density distribution of the electrons. Now you look at this. This is a functional that depends linearly on the external potential. Now let us try to apply Hellman-Feynman to that functional. I want to compute the functional derivative of E, that is the minimum of something, with respect to V, to its argument. What should I do? I should compute only the explicit derivative. So the derivative here has two contributions. You have the explicit derivative, that is the derivative with respect to V of the quantity to be minimized, contribution number one. This is the explicit derivative. Then we have the implicit derivative, that is the derivative of psi with respect to V. But Mr. Hellman and Mr. Feynman say that the derivative has to be disregarded at the minimum. So the derivative of this with respect to the argument V is just the derivative of the functional with respect to V. But the functional depends linearly on V. So its functional derivative, I didn't teach you how to compute it, but believe me, it's simple. This is linear, it's just rho, just the coefficient that multiplies V. If you do the exercise yourself, those of you who can, it's very simple. Those of you who cannot, you come to me and I'll show in 30 seconds how to do that, okay? So the density is the derivative of the energy, the functional derivative of the energy as a functional of the external potential with respect to its argument, to V. Now, this functional E of V has two properties. The second one I just described. The density is the functional derivative of the functional, and more or equally importantly, it is a convex function. I don't remember if it is convex or concave. Probably it is concave. I think it is concave. That is the its curvature has always the same sign. Because it is concave, dE over dV is monotonous. It is decreasing. But because it is monotonous, of course, the correspondence between the derivative and the argument is biunivocal, right? All the monotonous functions can be inverted. So because rho is the derivative of E with respect, it's the derivative of a convex or concave function with respect to its argument, then the correspondence between rho and V is invertible. Of course, to every V will correspond a density. This is again trivial because to every V will correspond the solution of the Schrödinger equation, and to the solution of the Schrödinger equation will correspond the density. Obvious. But because of concavity, the other way around would also hold. If you think it's exactly the same situation that holds in classical elementary thermodynamics, where the energy is a convex function of the volume, and because of this, the correspondence between the volume and the derivative of the energy with respect to the volume, which is the pressure, is biunivocal. So rho is a kind of internal property of the system that is conjugate to V, much in the same way as the pressure is an internal property of a gas or a liquid that is conjugate to the volume. And the fact that there is a biunivocal correspondence between pressure and volume, this depends on concavity or convexity, that is a consequence of thermodynamical stability. And in our quantum mechanical framework, the concavity of E of V is also a consequence of stability, because it can be demonstrated to be a consequence of the existence of a variational principle. I won't do that, but it's not very difficult. It is very instructive, to my view, very illuminating, the fact that this mysterious Hohenberg-Kohn theorem that say that the correspondence between density and potential is invertible is essentially the same thing as the relation between pressure and volume, or particle numbers and chemical potentials, or any pair of conjugate thermodynamical variables in classical statistical mechanics. It's exactly the same thing. Then you can go on, and because conjugate variables can be related to different thermodynamic potentials, you can play around, and the existence of the Hohenberg-Kohn functional, the universal functional of Hohenberg-Kohn, is nothing but the Legendre transform of E of V, exactly in the same way as enthalpy is the Legendre transform of the internal energy. And because Legendre transforms satisfy themselves a variational principle, you can express the original functional of the potential as the minimum with respect to all the possible densities of its Legendre transform, this universal Hohenberg-Kohn functional, plus the coupling with the potential. So this is the take-home message. the ground state energy of a system of interacting electrons in the field of an external potential V is the minimum over all the possible densities of a universal functional of the density, that is the Legendre transform of this, plus a linear coupling between the density of and the function. So we have arrived at the variational principle that is conceptually not so different from the Ritz variational principle we started from, but in which the variational functional variable, instead of being a monster many-body wave function that depends on an Avogadro number of variables, is just the density that is a quantity that only depends on 3 variables. It seems a great idea, and conceptually it is a great idea. In practice, the problem is that nobody really knows what the form of f of rho is, and the success or lack thereof of this brilliant idea will depend on our ability to give prescriptions on how to compute that Hohenberg-Kohn functional. Before doing this, actually, in a sense, this density functional theory relies on 2 theorems that we have stated. That is, the relation between density and potential is invertible, and the ground state density, the ground state energy can be expressed as the minimum of a universal functional of the density. 2 important theorems that would be void, and to some extent not so surprising, given the analogy with classical thermodynamics, if it was not for the next paper, not by Hohenberg and Kohn, but by Kohn and Sham, that introduced a very brilliant, a very clever way of thinking about this variational principle in such a way that would automatically suggest how to write down approximations. Let's do that. So basically, you write the unknown Hohenberg-Kohn functional, you split it into 3 terms. The Hohenberg-Kohn functional is the sum, basically, of the expectation value over the ground state wave function, which is unknown, of 2 things. The kinetic energy, the electron kinetic energy, and the electron-electron interaction. We don't know how to compute those, but we can just play around, jiggle a little bit, and write one approximate functional that is the kinetic energy that a system of non-interacting electrons would have if that system had the same density as the interacting one. We don't know how to compute this either, but you will see in a while that this turns out to be a very good ansatz. Then you have, so you have, in a sense, taken care of the kinetic energy. In a way or the other, you have substituted the real kinetic energy with something related that we hope will turn out to be useful. Step number 1. Step number 2 is to say, well, this is, we have the argument is an electron density. We want an electrostatic energy. How to get an electrostatic energy out of a density? Well, you compute the electrostatic self-energy, the classical self-energy of an electrostatic charge density distribution rho of R. Of course, this is not quite equal to the expectation value of the electron-electron interaction, but it is something that won't be much different. And then we have made 2 ansatz whose sum may be related to F, but it's not F. Then there will be something left out. And what is left out is something that is the smaller, the better the approximations, is the larger, the worse the approximation. And in any case, it's something that depends on our ignorance, on our fact that we don't we are not able to compute F exactly. So what is left out is the ignorance functional, is the functional that quantifies how much we missed out. This is something that Richard Feynman used to call the stupidity functional. That is the stupidity energy, the energy that is there because we don't know how to compute it. People less wit than Feynman would call it the exchange correlation energy. But in fact, the exchange correlation energy is the name we give to what we cannot compute. And so it is better called the stupidity energy, which we leave it indicated this way. Let us do the variational principle. The variational principle would say we differentiate this with respect to rho. And this is the same variational principle that would hold if the external potential to which our system is subject is not just the external potential, but it is the external potential plus the derivatives of this and that term. The derivative of this is what we call the Hartree potential. The derivative of that is what we call the exchange correlation potential. So here is what we end up with. So in order to solve this problem, we don't have to use density functional theory, because that problem we can solve with standard quantum mechanics. Why? Because it is a problem of non-interacting electrons, and we can solve it, provided we can calculate the effective potential that we call the Kohn-Sham potential, that as we have seen, is made of the external potential plus something that depends on the solution itself through the density. So basically, you have this set of self-consistent one particle equations that say that the density is the sum of the square moduli of one electron wave functions that have to be summed up to the point where their energy is smaller than the Fermi energy. This is nothing but the filling principle of Pauli, right? You have non-interacting electrons, you have to fill the independent electron energy levels up to where you have filled the proper number of orbitals, and each one of those wave functions satisfy the one-body Schrödinger equation. So if you can compute this stupidity potential, the potential that is the functional derivative of the exchange correlation energy of what we don't really know how to compute, then we could solve the problem exactly. So zillions of papers have been written about finding ways of approximating the exchange correlation energy, starting from the celebrated local density approximation of Kohn-Sham, in which they assumed that point by point the correlation energy could be written as the integral of a density of a correlation energy density, and that the correlation energy density locally would be the same that would hold in a homogeneous electron gas. Then, hence, the exchange correlation density, energy density would depend on the local density only. Then generalizations were introduced where this dependence was generalized to gradients and Laplacians, and then hybrids were actually were a very substantial step towards chemical accuracy. In hybrid functionals, there is a component of the exchange correlation energy that is remnant of the exact Hartree-Fock exchange energies, and there are many others that you will learn about in one of next days, probably tomorrow, if I remember correctly. So let me give 10 more minutes. I will steal 10 minutes of your coffee break. So how to solve these Schrödinger equations? One way that was the traditional way is to set up a self-consistent set of equations. So you have an equation to solve where the potential depends on the solution. So you guess the solution, you solve the equation. This gives you an updated version of your guess, and you iterate the cycle using sophisticated algorithms. So it's not trivial how to get this cycle to converge. But this is the traditional quantum chemistry way. In the mid-80s, when they were inventing their celebrated quantum molecular dynamics method, Karen Parinello came up with the clever idea that actually the ground state energy of density functional theory can be formally thought of as the minimum of a functional that, instead of depending on the density, depends on molecular orbitals, on individual wave functions. And you can write down this functional in this way. You have here the one particle kinetic energy. You have the interaction with the external potential, Hartree, and exchange and correlation. And basically what you have to do is to minimize this functional with respect to all the possible one particle wave functions that satisfy the constraint of being mutually orthonormal. If you do this, you write the Lagrange equations. Basically, you minimize this by imposing this constraint. You have Lagrange multipliers that take care of the constraint, and because this matrix of Lagrange multipliers is symmetric, then you can, and because this functional is invariant with respect to unitary transformations in the space of occupied orbitals, then you can write down, you can go to the basis that diagonalizes the matrix of Lagrange multipliers, and you go back to the standard self-consistent type of equations. But because these equations derive from a variational principle on the individual molecular orbitals, you can solve it in two ways. Basically, in both ways, you represent a wave function by a linear combination of basis functions, and in this course, we will use plane waves. So the variational principle is a variational principle for these coefficients because the basis set remains fixed. So the solution of this variational principle in the form of a self-consistent cycle will go over the self-consistent solution of a matrix eigenvalue equation where the matrix to be diagonalized depends on the solution itself, or, and this would be the traditional quantum chemistry way, or you can directly minimize this functional. So there are many ways that you can minimize a complex functional, but the first one to be exploited by Carrer-Parinello, which is not particularly efficient, but it is robust and so easy to describe that I will spend a few seconds to tell you what it is about. Functional minimization is all about finding the lowest level of some objective function, right? Suppose you are in a mountain landscape, and you are on the top of a mountain, and you want to go down to the bottom of the valley. What would you do? You just sit on the snow, and you let the gravity slide you down to the minimum. You not necessarily hit the absolute minimum, but when you will stop, this will be the minimum, right? Or local minimum. What is the equation of motion of you sliding on a snowy slope? If there is friction, and there is friction, right? You don't accelerate infinitely. Your velocity will be proportional to the force because of the friction. So if you write down an equation where the velocity of the coordinates here are these coefficients, are proportional to the force. And the force, what is it? It is the derivative of the energy with respect to psi, plus the forces that are due to the constraints. The constraints may be, for instance, if you let a ball roll down, the constraints will be what keep the shape of the ball spherical while it is rolling down. So a ball that is rolling down, if in the high friction limit, will have a velocity that is proportional to the force plus something that keeps the shape of the ball intact. When it stops, it will stop at the minimum. This is the method of steepest descent that is not very fast, but it is very robust, and it is implemented with some of its more sophisticated variants in quantum espresso. As it often occurs, I miscalculated the time it takes to me to lecture, actually because I miscalculate the amount of chats that I make. So I will not say anything. I wanted to give some general qualitative introduction to the concepts of plane waves and pseudopotentials, leaving then the floor to Ralph. But do I understand correctly that it is fine for you that I stop here and you can take over with plane waves and pseudopotentials from scratch? Very good. So this is an appropriate time for me to stop. Let me conclude by wishing all of you a very successful and even more pleasant stay with us these 2 weeks. And let me reiterate the recommendation of not being shy. If we are not clear, you interrupt us. If you are really not clear, we interrupt us. Or if we are clear, but your background is not enough, that's equally good. You interrupt us. If you don't feel like that, you come to us individually in the coffee breaks, in the afternoon. If you don't find us by email, my own email is simple to remember. It's my family name at my my affiliation.it. So if I am around, you stop me if you want to talk to me. If I'm not around, you drop a line of email, and I'll show up a few hours later. Okay? Thank you very much, and enjoy the school.